guys, welcome to the April 20th lecture here on climate change. This will be the last lecture of new material, not only for test 3, but for the entire year. Woohoo! Celebration. All right, so we're talking about climate change today. And the key things to remember about climate change is first, make sure you know the difference between weather and climate. So just a reminder, weather is extremely short term. It's what's happening in one particular place at one particular time and constantly changing. We remember those things like this, all right? You can get cuckoo crazy nut extremes in weather. You can get extreme rainfalls, extreme lack of rainfalls, extreme temperatures. You can get crazy weather events that don't normally occur for a region at all right? But that's all weather. Climate, however, this is a long-term type of thing, all right? You're looking at about 30 years worth of just averages for a particular region, all right? And all those cuckoo crazy nut extreme things that might have happened for one day or 1 year or possibly even 2 years or 1 month or something like that, those are going to get basically just canceled out in those averages, all right? So climates are basically much more stable. It's just the normal weather patterns for an area, okay? So now climates do change. We know that, 10,000 years ago, climate was very different. Things were much colder. We're in an ice age back at that time and stuff like this. So what is it that causes climates to change over a long period of time? Now, most of these natural causes occur over thousands, hundreds of thousands to millions of years for them to go on. However, there are a few causes that are very few that are natural, but a lot of man-made stuff that can cause climate change as well. So we'll talk about these a little more detail. Now, the very first one on this list is called the Milankovitch cycles, all right? And what these are referring to are some orbital cycles that occur with our revolution around the sun. So now, you don't have to worry about any of the details of this. Just know that we've got some variations in our orbital as we go around the sun situations. I know I told you at the beginning of the year and stuff that will show up on your final exam. We know that the shape of our orbit is an ellipse as opposed to a perfect circle. We know that we are closer to the sun in January than we are in February. We know that the Earth tilts at 23.5 degrees. And we also know that the North Pole is pointing toward Polaris, or what we call the North Star, right? And for us, all of that is totally legit. However, in reality, there's a little bit of variation. So let me just show you a diagram a little bit of these Milankovitch cycles. Milankovitch was a scientist about 100 years ago that figured out these differences. So there's differences in the shape of our orbit. It's always going to be an ellipse, but sometimes it's a more elongated ellipse. Other times it's maybe closer to a circle shape. All right, that's going on. That's, I think, 100,000 year cycle or something like that of where it varies between that. We've also got differences in the tilt of the axis and also where the axis is pointing. Basically, the Earth tends to wobble like a top that you put into spinning on a table, and then as it starts to slow down a little bit, it starts to wobble. All right, and then also tied in with the shifting of where the North Pole is pointing can actually change where perihelion and aphelion are at different times and stuff like this. So let me just kind of demonstrate some of these a little bit more. So here you got the globe, all right? So again, the shape of the orbit, as we know, is a bit of an ellipse, all right? But sometimes, I mean, it kind of wobbles, goes from more straight to more elongated and back and forth like this, all right? And there's a cycle, again, about 100,000 years, something like that cycle for this. The Earth is, in reality, very slowly, over the course of about 41,000 years, so this is not something you can observe over the course of one lifetime, but the Earth is, not only is the tilt changing, goes from about 24.5 degrees off max up to about 22 degrees, all right? Right now we're up like right in the middle of that, but it's also wobbling like this, all right? So at different times we're pointing to different areas, okay? So the tilt changes as this goes on. These are something around 40, like I said, 41,000 year cycles. So we're not always pointing toward Polaris. And this, FYI, this is one of the reasons that are the horoscopes where it talks about, you know, what star constellation is rising in August and stuff like this. Well, when they were put into play about 1,500 years ago, we weren't actually pointing to Polaris. We were pointing off a little bit. And so the stars are not aligned the way they are when the horoscopes were written up or whatever, when they came up with those ideas about what star sign you were born under and things like this. So that's one of the reasons they're lots of fun, but they are not accurate by any means. All right. So now one of those cycles in and of themselves may not cause any change. But if you end up being tilted more, plus you're closer to the sun when you're tilted toward the sun, could make things hotter or colder on the opposite end. There's a whole lot of different ways that these guys can add up, because again, the cycles are not, you know, even. That goes on, but that is something that you know, if they work together to be an extreme, might possibly cause a change in insolation at different times of the year, and possibly cause climate changes as a result of that. So that's a play that it is in there. But there's other factors as well, and they all work together to either keep climates the way they are or possibly make a full change. So another one that you'll see on here is changes in the land configuration, all right? So this can be the continents themselves moving, which I'll show you in a minute. It can be islands forming or disappearing. It can be mountains forming or disappearing. And of course, this is natural. This occurs. It's part of plate tectonics. These occur on a very long time frame, hundreds of thousands to millions of years. But one example based on that is, you've probably heard of Pangea. About 200 million years ago, in the days of the dinosaurs, the continents of the Earth were actually all squished together in one big supercontinent that we called Pangea. All right, very different layout than the way the continents are today. So we know about how land and water relationships can factor into climate. We also know how if you're in the middle of a continent, that things tend to be much more dry and also a bigger range of temperatures. Well, when you had Pangea, when we had all the land masses all just squished together in one big continent, that left not only both the North Pole and the South Pole free and clear of any type of land. All right, you could expect things were possibly much drier in a lot of places because you had a lot more interior types of land, all right, that went on and stuff like this. Now, plate tectonics split these guys up. They started to, pull apart and eventually reached the configuration we have today, probably over the course of about 150 million years, but this configuration that we have today is very different from here. One of the things that's very different about this configuration is, let me switch to the actual globe, is that the polar areas are not free and clear, all right? So even though we don't have any land at the North Pole, the Arctic Ocean is still pretty much contained by the continents. There's not any large passages from these extremely cold polar waters. You know, for them to get out, it's pretty difficult, all right? It's not free and open. And of course, we know at the South Pole, we've got a big giant continent sitting right on that coldest area. So this circulation of water down there is not as much, all right? So that's going to keep the polar areas a lot colder the way they are now, because the warm water is not as easy, you know, doesn't have the access to the super cold areas, and the cold water doesn't have the access down to the warm areas. So we still have circulation going on of warm versus cold, but it's not near as complete as you would have if you didn't have any land, I mean, at the poles, all right, where those cold waters can completely go around, and that means you're not going to have the cold extremes, all right? So that's one way. And again, those are happening on the millions of years times scale that can go on, all right? We've had, in the history of the planet, Pangea, again, was in place about 200 to 300 million years ago. Well, prior to that, about 600 million years ago, there was yet another supercontinent where things had come together and split apart. So they're constantly moving on things like this. Now, mountains build up, all right? The Himalayas are the result of plate tectonics. We know how the Himalayas themselves can block some like cold fronts and stuff coming down, but the Himalaya mountains, which occur right here above India, all right, are the result of the Indian subcontinent smashing into this area, all right? And we know about rain shadows and stuff like this. The Appalachian Mountains, all right, and the Alleghenies, everything that's over here on our east coast, these are really, I joke about them being kind of wussy mountains because they're not very tall. Well, 600 or so million years ago, they were as tall as the Alps, all right, or as tall as our Rocky Mountains. But they're extremely old now. They've gotten worn down, so that is a change. The Rocky Mountains themselves, which we know is a bit of a border to some of the west coast weather patterns going further on inland, those are fairly young. There's only a few million years old, all right? But once they popped up, thanks to some fault systems, all these mountains have affected the weather in the interior of the land over there, all right? We have volcanoes that pop up and can cause mountain ranges to form, you know, fairly quickly on a geologic time scale, okay? Still like over the course of hundreds of thousands to a million years or so, all right? So that can happen. Okay, now people, however, can also cause changes in mountains and land configuration and stuff like this. We can actually shear down the levels of some mountains. That's called strip mining, where they literally take the top of a mountain off and lower areas like that. So, you know, and that's, again, those are some big issues, especially in the Appalachians and Allegheny Mountains and stuff like this, and other places in the world that are going on. We've talked about deforestation, which can change the albedo of areas and can take areas that are rainforest tropical climates and change them into something else, because you change the cover, you change the albedo, you change the moisture content. We know about how many trees help produce, you know, are big producers of water vapor. So you take all the trees away, you're not going to have as much moisture. Things are going to get drier. we can fill in wetlands. We do that all the time, sometimes in small scale, but they're still doing it around here. So that's going to decrease amount of moisture available in areas. You've got desertification, which we talked about, where you take lands that are right on the border dry, the steppe lands, and either overgraze them, do poor farming practices and things like this, and it literally makes it shift to an out and out complete desert, unable to support hardly any type of vegetation that goes on. That's all on us, all right? Our Midwestern areas are experiencing a severe drought. It's going on multiple years now, and how much of that is natural, how much of it is, again, due to our farming practices, our diverting streams and waters away, from their natural courses to irrigate just, basically some cities and stuff like this. It could be. Now, a fun thought process or practice that you can think of, it's possible for us to actually take deserts and bump it up to a slightly more humid area. I mean, we can improve the climate as well. In California, in Palm Springs, it's a desert, out and out pure desert area. However, we have built lots of golf courses and resorts and put in swimming pools and stuff like this. Well, those golf courses, they're grass, they require a lot of irrigation. And so people are artificially bringing more water into the area. They are growing plants that are not native to the area. These are plants that do require a lot more water. But in turn, we know about we know about transpiration from the plants. So the more plants you put into an area, the more water vapor is actually put out into the air. And so the area around Palm Springs, over the course of like 15 years, it has gotten like an inch or two more rain than the surrounding desert areas. So given enough time, possibly, we could maybe terraform the desert and turn it into more of maybe a steppe land or something like this. But of course it goes the other way, all right? You can take steppe lands and change those up and, again, turn those out into deserts as well, okay? But that's something that's going on. Other things that you can see an increase in aerosols. That's the solid particles, itty bitty, but still solid particles that are up in the air. Some of those can absorb heat. A lot of them actually reflect heat more than anything. We usually see these, they can occur both naturally. Volcanoes are the #1 instance of that. And they will, in fact, it was Tambora, which was in Indonesia, that was one of the biggest massive explosions of a volcano ever. It was in, I want to say 1823, in 1820s. Anyway, it threw so much dust and ash and sulfuric acid, which is a naturally occurring chemical, up into the air. And it got literally all the way up into the stratosphere, circled the entire globe, and caused a lot reflection of insolation. And so for 2 years, there were much cooler temperatures on the planet. And in Europe, for example, it was known as the year without a summer, because even in July and August, some of the lakes were freezing over at night, and they didn't even have a frost-free season. All right, but again, that was a very short-term type of deal. But if you have a huge increase in volcanic eruptions, for example, like we had actually prior to the days of the dinosaur and stuff like this, that throws a lot of aerosols in. But at the same time, they're also throwing CO2, which we know is a greenhouse gas. So that ties in with a change in percentage of greenhouse gases. So there's a lot of things at play. Does it even out that you have more greenhouse gases to trap heat, but you've got ash clouds and dust clouds to kick heat out? It's what balances. I don't know. Again, point being, there's lots and lots and lots of variables involved with this. One thing with the aerosols, I was just reading an article today describing about, because a lot of our poor farming practices and the desertification that is happening, that causes a lot more dust into the air, which can reflect a lot of insulation. So it's like, ooh, is that would that be our answer to the to make the earth cooler over time? Yeah, we'll pump more dust into the air. Well, of course, that comes with lots of issues as well. There are air quality issues as far as breathing goes. That's another issue that we've got now with people having asthma and stuff like this. It's one of the big problems that I have with this current presidential administration, because they are relaxing all the, not only the clean water, but the clean air rules. And they're even at this time, they're saying, with COVID, it's too much trouble for any factories to actually adhere to clean air rules. So we're going to let them lax so you can pump out as much as you want. Yeah, that's really good. Being able to breathe clean air couldn't be good for your health at all. So, crazy things like this. Anyway, but yes, those changes in greenhouse gases. This is both naturally occurring and man-made. Again, those volcanoes, all right, when tons and tons of volcanoes were erupting at a much higher rate, and many more volcanoes. Again, back in the days of the dinosaur, yes, there was actually more CO2 in the air than there is today, all right? But that's because the volcanoes back then were much sore. There was a lot more going on. Let's see, what was it? Temperature increase back in those days of the dinosaur. This is mid-Cretaceous. This is just strictly FYI. Temperatures were anywhere from 9 to 27 degrees Fahrenheit warmer than they are today, all right? Sea level, the ocean levels were higher, about 650 feet higher than they are today because of that, all right? Things were much warmer back then. They didn't have all the glaciers that we had back then, all right? So, however, today, the greenhouse gases that are increasing in the atmosphere are due to us, all right? There is no question that we are dumping and pumping all the methane and all the CO2 that is going in. Now, as part of this warming that has occurred, all right, for example, okay, I just looked it up, and the top 10 hottest years on a global basis, we're not talking about one particular region, but on a global basis, have all occurred in the past 15 years, all right? So and then ever since 2013, it's been every single year has been in the top 10, all right? So we are providing this type of thing. Now, with the warming that we are seeing lots of areas, as we know, in the tundra where they have the permafrost. Those areas are warming up. The permafrost is melting for the first time in millennia, since we've been keeping records. Trapped in that ice is a lot of naturally occurring methane. And now that methane is being released into the atmosphere. So yes, that's natural, but its release at this time and the quantities is unnatural, okay? Because it's due to the initial warming by the excess CO2 that we have pumped into the atmosphere, along with the methane. Methane is, even though there's not as much methane as CO2, methane's a much better absorber of heat than even CO2 is. So it, takes a lot less methane to warm things up than it does the amounts of CO2 that go on. Now, tied in with all of these, which are working all either for each other or against each other, is what we call the feedback mechanisms that go on. This is where one thing leads to something else, which leads to something else, which leads to something else, similar to the methane that I just told you about. Another example for this is if the Earth got covered by 50% ice, would be a turning point where everything would get colder and colder. So basically, all right, you start out, you know, we've already got snow-covered regions up here, all right, and they used to be all year round. The past, 5 years? For the first time, we've been having all that ice melt up here, which is going to warm things up, because we know ice and snow, being white and usually smooth, has a very high albedo, so a lot of insulation is reflected right back. All right, so imagine you've got that. Things are cold enough to be frozen up here. So all that snow and ice is going to cause the temperatures to drop thanks to the albedo and reflection of sunlight, which makes things colder, which means you can have more snow and ice, which is going to reflect more insulation, which is going to make things colder, which means you can have more snow and ice working its way down, permanent ice. And you get to a point where even though you're in the tropics, you've got so much snow and ice covering that you can even get snow and ice and frozen seas all the way down to the equator. And in fact, we've hypothesized, there's more and more evidence pointing to this, that this did happen once upon a time. It was probably around 900 to 600 million years ago. And it's called the snowball Earth hypothesis, all right? And basically, yeah, that's exactly what happened. How did we break free of that? More than likely, a volcanic activity that finally started warming things up and pumping some more CO2 into the air and warming things up, and it went back the other way. Now, talking about that snowball Earth, that would be what we call an ice age. Okay, now everybody's heard of the ice age. You've seen the movies, all right, and you know about the mammoths and the mastodons and those big old guys, and you usually talk about the cavemen and Neanderthals that lived at that time, or whatever. We know all the stories. Well, basically our planet does go through times of where you either have an ice age or you don't. What an ice age is simply defined by the fact you do have cold enough sustained temperatures on a yearly basis for large ice sheet, ice cap style continental glaciers to form, all right? And so that requires colder temperatures. Today, we have those continental glaciers. That's what covers up Greenland, right up here, all right? And again, these are covering the entire continent, all right? At their thickest, they're about 1 to 2 miles thick. Same thing, Antarctica. Most of Antarctica is covered completely by these ice sheets. Okay, so that's what we mean. And at times, the glaciers can extend much farther down, all right? The last ice age that you often hear about was when the glaciers peaked about, roughly speaking, 10,000 or so years ago. Let me show you a pic of North America. It's not a picture, it's a diagram, because of course there were no cameras back then. But this is showing you how much those continental glaciers covered, all right? When we talk about glaciers, it refers to on land. You can also have sea ice at this time, but those are not actually a glacier. Okay, glaciers have to occur on land. But you can see basically all of Canada was completely covered, all right? We had glaciers that came down in the U.S. The Northeast, everything from Maine down to New York was completely underneath a giant, again, 1 to 2 mile thick sheet of ice, and it came down as far as like St. Louis. Now, for even the rest of America here, temperatures were much colder. I mean, if you've got you've got polar climates that are, as far, here at St. Louis, that means our temperatures here, we were basically microthermal temperatures back at that time. We find fossil fir trees and spruce trees, the same type of trees you would find, say, in Minnesota. We find those down here. So yeah, it was, much colder. I'm sure we got lots of snow in the summertime, in the wintertime, which then melted, and we had some mild summers, but it was very, very different that goes on. Now, one thing you may notice is here's Alaska, which we know is, still cold today and have areas of permafrost and stuff, but they were glacier free. And the same thing happened over in Eurasia. Of course, most of Europe was covered by glaciers, but good old Siberia, which we know is extremely cold, that we've talked about, this, huge area right up here, this was actually pretty much glacier free. And the reason for that is what we already know, is that it's fairly dry, all right? And there just wasn't enough snowfall on a yearly basis to build up those thick glaciers. That's what glaciers are made from. They're made from snowfall that falls and doesn't melt over the course of a year, and then you get more snow that falls on top of that, and it gets layers up, and it's the weight of the snow on top that compresses the snow on the bottom and turns it into ice, and it turns into an ice sheet. That's how they work. So you've got to have an ample amount of moisture available to get the snow to make the glaciers. So this area, it's dry today. Lots of these areas are dry, and it was dry then. So there just wasn't enough, it was cold enough, it wasn't enough moisture to make enough snow. And that's the same thing that happened in Alaska, all right? Or, those areas up here in Alaska, it was too dry for those to occur, all right? Now, like I said, the planet has had multiple ice ages. You do not have to know these dates. This is FYI. We are pretty sure there was one like 2.3 billion years ago. There was that possible snowball Earth scenario up to 600 million years ago. Then there was another one about 400 million years ago, 300 million years ago, and then one that started about 15 million years ago and is still going on. This is a key thing to know. We are still in an ice age. Remember I said to be considered to be part of an ice age, you have to have some continental, large-scale, sheet-style glaciers. And we have those still today in Greenland, all right, it's still covered, and then again also in Antarctica. Therefore, we are in an ice age still. The same ice age that's been going on for about 2.5 million years. Now, over the course of that 2.5 million years that goes on, there are peak periods where it's much colder and you have much larger expanses of glaciers, and then you have some warm periods where many of the glaciers retreat and go away, but then it usually gets cold again. This is very roughly speaking the warm spaces. They call them interglacial because you don't have as much glaciers going on. Those very roughly last about 10,000 years. And then the full glacial periods where they can wax and wane last much longer, and then you'll have a little, warmer spell. Now this is what's kind of interesting, all right? Now the last glacial peak ended about, roughly speaking, 10,000 years ago, okay? And so here I said about 10,000 years. And so we were experiencing and expecting things to start getting colder again as we headed into a much bigger glacial period within this same ice age. And up until about 1850, things were getting colder, all right? And this was absent the big giant volcanic eruptions in the 1800s that went on with Krakatoa and Tamboro and stuff like this. But yeah, there was okay. So I'll get these dates for it. Again, you don't have to, this is all FYI, it's just interesting that goes on. So we had a warmer, very warm period from about 900 to 1200 AD. This was when Greenland was named Greenland, even though it's totally covered by glaciers, because the glaciers had retreated a little bit, at least, back up into the highland areas and stuff like this. The Vikings settled Greenland and had year-round residences, and it was, they were able to farm and raise sheep and goats and things like this. But then things started to cool off, and the fall snows started arriving earlier and earlier and lasting longer and longer into the spring, and so their growing season shrank, and there were probably even some summers where they still had frost occurring. The permafrost started staying frozen closer to the surface longer, and they were no longer able to grow enough food to survive, and so they abandoned the area and went away. So it was known as the Little Ice Age, and it went from about 1400, all right, up to about 1850, all right, and then all of a sudden things started to warm again. Well, I doubt that it's a coincidence that right around 1850 was right at the peak of when the Industrial Revolution started booming. This was when we started using the fossil fuels. Of course, initially it was coal in Europe, running the textile machines and stuff like this, and then eventually, we had coal that, as it spread around to run all of our engines and things like this, and then of course we picked up with the other fossil fuel. Coal's fossil fuel, all right, it's made from the ancient remains of plants and stuff like this, but same thing with oil, and the fact that, we were expected for things to be cooling off, but instead we've seen a steady increase since 1850, and then of course the past 20 years, temperatures have really, 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 really warmed. Now again, you can have a crazy year. You can have that crazy year when timber exploded and caused temperatures to go down so much that, again, it lasted over the course of about 2 years. That's not enough to actually change climates. Pinatubo in the Philippines, it was 1992, I think it was. That was another massive explosion that put tons of dust into the air, gave us some beautiful sunsets for about 2 years, and also lowered the global temperatures by a couple of degrees for at least those 1 or 2 years. But then, it dissipated and things kind of went back to normal. So, but we have seen this trend extremely, that goes up and up and up and up. And so, climates are changing. We're having climate change that is occurring right now, all right, because things are warming up, and it is a result of man-made. Because all these other incidents that can occur on a natural scale, they take thousands and thousands of years to fully manifest, all right? But just this, 150 to 200 year quick change that has gone on, that's on us, okay? We're the ones that are dumping all the CO2 and the greenhouse gases. That is, and we're doing the changing with the deforestation and the desertification, I'll get it right in a minute, and all these types of things that are going on. And of course, they in turn are triggering some natural phenomenon, like the release of the methane from the permafrost areas and stuff like this that is going on, all right? But key thing to take away is we are still in an ice age. We're just in the warmer interglacial period, but we are still in an ice age, all right? So you can freak out a lot of people if you want to talk about that type of thing that goes on. Okay, that's about it, all right? Be aware that climate change does happen. It generally happens very slowly. It never happens overnight or over the course of even 1 to 2 to 10 years. Now, something else to keep in mind when we're talking about the current climate change that is occurring with the entire global average temperatures going up. That doesn't necessarily mean our climate is going to change. We're going to be mesothermal, humid subtropical for the foreseeable future, all right, within your lifetime. Our summer temps might get a little warmer, all right, but you know, we're not gonna be pure tropical by any means. That goes like this. So basically what's going to be changing is not so much the climates of the entire world, but, well, I have the right book here. All right, let me find that, if I can find that climate map that goes on. It's the borders that are going to be changing. So when you look at the entire global map for climates that we have now, what's going to be shifting and where you're going to see the greatest amount of true change is at the borders. Of course, we know the borders themselves are big, wide transition zones anyway, okay? They're not a cut and dry, razor sharp line. But we're going to be seeing desert expanding, all right? We already are seeing the boundary like between the still microthermal, but going from what was a subarctic type situation up to maybe more of just the humid continental. Or we're seeing tundra areas that are becoming more of the subarctic. Okay, that's the issue, and that's where we're seeing the biggest changes is in these polar areas where they're warming up and where they're crossing the threshold from the 32 degrees, making the big difference between frozen lands and not frozen lands, between getting ice and getting rain, or getting snow and getting rain, and things like this. That's where this change in climate is so much obvious and going on. They're still cold up here, all right? Even in areas that have switched, that are maybe more temperature regimes of a subarctic climate versus a tundra climate, it's still freaking cold. And in the wintertime, it's still going to be frozen over, okay? Again, it's not turning into a tropical paradise up here, but it is making a huge difference with the melting of all this ice, okay? Especially the permanent ice, which is going to encourage more insulation to be able to make it in and be absorbed, which is going to make things warmer, which is going to cause more ice to melt, all right? We're seeing a huge effect on the wildlife that is up here. We're seeing a huge effect on the populations of people who live in these areas. Up here in Canada, all right, on this side, that's over here. For the first time, folks who live on the Arctic Ocean areas, that's normally tundra, they are having wildfires, all right, for the first time ever, because things are drying out for the first time ever. They don't even have a word in their, I don't know if these, be the Inuit or Aleutian or I don't know, whichever the native language is, they don't have a word for wildfire. All right, because fires do not occur naturally. Usually, they rarely get thunderstorms to get stuff started by lightning. And so, yeah, there's never been a word for that, but they've been having, the past 2 summers, they've been having wildfires for the first time, having to deal with that. We know the polar bears are probably going to become extinct in the wild just due to the fact that, especially in the summer, all the ice flows are melting, and that's what they fish off of. All right, and so that's how come you're hearing more stories about polar bears going in and raiding people's garbage cans and things like this, trying to because they're starving, they're looking for food. So that's a big issue. But that's what we're going to be seeing. We're going to be seeing desert areas that are expanding. We're going to see steppe lands that are going to cross the threshold and become more desert lands. All right, we're going to see possibly savannas that may turn into out and out steppes or something like this. All right, so it's those border areas that are going to be seeing the major changes. All right, that goes on. So things to keep in mind. So this week, all right, is also the week for test 3, which is covering the severe weather and all this climate type of stuff. So today I will be sending you guys the email that will have the test 3 test on it. All right, so you've got all the time in the world to look up the answers, and I will post the actual online test. It'll be there Wednesday morning. You will have a limited amount of time to take it, a little over 2 hours, but again, you're not taking it cold. You do all the answers on the written sheet that I'm going to send you, and then just transfer them onto the online version, okay? Because it's the same test questions, same order, answers are the same order. And just like I did last time, I have some of the questions I've either reworded or added some extra explanation onto them to hopefully make things clear. So if you've got a confusion about a question, when you get to it on the online version, I'll have answered. I'll have specified so you can go, oh, okay, I gotcha. So, but it's the exact same question. The answer is going to still be the same as it was to the matching question on the written test. Okay, so that'll be up. You can take it anytime Wednesday, Thursday, or Friday night. Okay, so take it during those times. That's when you're done. I will accept it late. However, you will get 10 points automatically taken off from whatever your score is. All right. Now, next week is our last regularly scheduled class, all right, which is just going to be a fairly short lecture on how to review for the final exam. All right, so that's still going on, which it's comprehensive. It's everything we've talked about, just like we've talked about it in climate. That's what the test is. So it's not starting from scratch, but I'll talk more about that. You've already got all your study guides to look at. You've got your test 2, and you'll have test 3 copies to look at. I'm even going to make test 1 available for you guys to look at. I'm going to stress it now, I'm going to stress it later, and I'm going to stress it even later. The final exam is not the exact same questions that have been on test 1, test 2, or test 3. It's the same concepts, all right? But I might have asked about high pressure cells on one of your tests, and this time around I'm going to be asking about low pressure belts, okay? So you've still got to know everything. So you can use the past test as just a guide to what's the type of stuff I need to study, but don't just learn that the answer to number 6 was B, because you're not going to see that on the tests, on the final exam. Final exam, I am not sending you a copy, okay? But you'll have plenty of time to take it. I'll be taking it just like you normally would have, all right? Except you'll have the advantage here, taking it home, you'll be able to have your notes, your books, your study guides available. But do not plan on looking up every single answer. There's 100 questions on this. If you try to look every single one up, you're going to run out of time. So you need to study for it just like it's a regular old closed book test, and then that way, you can zip through them. If you're unsure about a couple of questions, you'll have time to maybe, let me look up and make sure I'm, got it straight. Which one's high pressure, which one's low pressure, which way does wind blow? I'm freaking out. I can't remember. I've gone blank. You can look that up. But again, you need to prepare for it like a regular old closed book test, and just, be woohoo. I can look up a couple of questions I'm not sure about. So more to that later next week. For now, worry about test 3. All right, you got this. Again, it's all information you've had before multiple times, putting it all together. All right, so see ya. Have a good week.